Building a modern social feed requires operating at a scale that breaks traditional database architecture. We are looking at a baseline of 300 million daily active users, generating roughly 500 million new posts every single day. On the consumption side, those same users request to read their feeds 3 billion times a day. That creates a staggering imbalance. Platforms are intensely read-heavy, operating at ratios between 100:1 and 500:1 in favor of reads over writes. And every single one of those 3 billion read requests has a strict latency budget. The system must fetch, assemble, and deliver the feed to the user's device in under 200 milliseconds. Guaranteeing that speed creates a difficult trade-off. Delivering a feed in milliseconds requires pre-computing data before the user even asks for it. However, synchronously assembling feeds for millions of users every time someone updates their status creates a massive write bottleneck. To see exactly how these bottlenecks are solved, we are going to design an industrial-scale activity feed from the ground up. The foundation of this system rests on two theoretical models for data dissemination: fan-out on write, commonly called the push model, and fan-out on read, known as the pull model. Deployed in a pure, standalone form, both of these models will fail in a production environment at scale. Instead, modern systems solve the paradox by using graph-aware hybrid architectures that dynamically route data based on user profiles. Mastering newsfeed architecture requires looking past basic database selection. It requires understanding network topology to successfully bound both read and write amplification. Let's build the push architecture. User A's published post flows through a load balancer, web server, and into a primary database. A fan-out service then queries a graph database for followers, publishing tasks to a message queue. Fan-out workers asynchronously append a mapping of the post and author ID directly into each follower's timeline cache. These materialized caches are stored in memory, utilizing Redis sorted sets to maintain strict chronological order. That covers the write path. Now let's see what happens when a follower opens the application. This diagram shows the algorithmic efficiency of the push model. Retrieving the feed is an order-of-1 time complexity operation. It requires a single direct cache lookup to fetch the IDs before hydrating the content. This model shifts the computational burden to the write phase. Pre-computing data keeps the read path fast enough to meet our latency budget. However, this architecture assumes a relatively uniform distribution of followers, which does not reflect how social graphs actually function. Take a high-reach account, like Elon Musk. When a user with over 100 million followers clicks publish, under a pure fan-out on write model, the system attempts to execute the exact same workflow. This triggers massive write amplification. A single post forces fan-out workers into 100 million simultaneous cache inserts. Message queues back up, the write tier saturates, and regular posts are delayed. Engineers call this bottleneck the celebrity problem, where pure push architectures physically break down. Tying your system's write amplification strictly to a user's follower count is an unsustainable architectural choice. To eliminate write amplification, we can propose the inverse architectural solution: fan-out on read, or the pull model. The write advantage here is quantifiable. A celebrity post is written exactly once to a global database, achieving order-of-1 write complexity. The write tier is protected. But we have to evaluate how a user actually views a feed if nothing is pre-computed. This shows the mathematical reality of the pull model. The system queries the database for recent posts from every followed account, executing a massive in-memory merge sort. This multi-key query exceeds the latency budget. Furthermore, because timelines are unique, results cannot be effectively cached. While the pull model protects the write tier, it pushes the computational burden onto the user's loading screen, making it unviable as a standalone design. The solution is the hybrid edge merge architecture, establishing a dynamic celebrity threshold. Users with fewer than 10,000 followers operate on the pull model, fanning out writes to materialized caches. Users above the threshold bypass the fan-out queue, writing posts to a dedicated celebrity cache. The real engineering happens at read time through a process known as parallel edge merge compilation. When an app opens, the client requests the pre-computed push timeline, while the server simultaneously pulls recent posts from followed celebrity caches. These distinct streams undergo a timestamp-sorted merge at the API edge, creating a unified feed before fetching heavy media assets. But there is a gap in this design. We have to account for what happens when an inactive user logs in after a month away. This requires a cold start fallback. If a user's push cache has been evicted due to inactivity, the system executes a one-time fan-out on read across their entire followee graph, bootstrapping the cache for all subsequent visits. The hybrid model accepts higher architectural complexity in exchange for successfully bounding both read latency and write amplification. The scaling heuristic for distributed data is clear. If writes are your bottleneck, utilize pull. If reads are your bottleneck, utilize push. Surviving massive real-world viral events relies entirely on intelligently combining these paradigms to route around network congestion in real time. Up to this point, our baseline architecture assumed a simple reverse chronological sorting mechanism. However, modern platforms utilize machine learning and sequential recommenders to rank feeds by relevance rather than pure time. This diagram shows the current production standard. The edge merge passes its candidate posts to a machine learning model that scores them based on engagement probability and user embeddings, reordering the feed just milliseconds before delivery. Regardless of how advanced AI algorithms become at ranking and recommending content, delivering those insights to millions of users instantly still depends on mastering the fundamental computer science of push and pull.